So in our last video, we figured out what our general power formula is. And I call it our general power formula because it can be used for any calculation for power. It is the formula for power in general. But when dealing with electricity, there's another way to write this formula, another way to calculate power, let's say. So let's say this is our electricity power formula, and we'll go ahead and write that one out as well. It's super simple. It's just power equals current times voltage. And there is a proof that shows that these are the exact same equations, but I'm not going to bore you with that math. If you would like, you can challenge yourself to figure it out yourself, or you can look it up or find out the proof online, whatever you want. For now, just trust me that those formulas are both versions of the same power formula. With that, let's go ahead and look at an example applying both power formulas. Let's go ahead and say we have a remote control toy car. Let's go ahead and draw the wheels here and draw the back. And I know, it's just so beautiful, but let's go ahead and just label this as a toy car. Just a remote control car, and let's keep our numbers simple. Let's say this is a 100 Newton car. And let's say it has some battery pack on the back that powers it, so that makes this little remote control car drive. And let's say that this battery pack is 7.2 volts. Let's make sure we label this little box-shaped thing as a battery pack here. And let's say we run this car, this toy car, this remote control car for 10 seconds. And when we do, let's say it travels, just keep our numbers nice and simple. Let's say it's 6 meters. Let's say the current running through this battery pack while it's doing this work is 11.1 amps. So there's a few things to unpack about this problem. Let's go ahead and start by using our new formula here as the power that's supplied from our battery pack. So we'll go ahead and say, what is the power inputted from our battery pack? So let's just say, what is the power input? Question mark. And to figure this out, we'll, of course, just use our formula here for power for electricity. We'll say power in, though, since it's the input. And we'll say that it's equal to current times voltage, which we kind of just wrote out. We already know what those two numbers are. The current is, let me pick the right color here, is just 11.1 amps. And our voltage is just 7.2 volts. And I'm bad at math, so we'll pull out our handy-dandy calculator. We'll just say, what's 11.1 multiplied by 7.2? And what do we get? We get 79.92. So our power input equals 79 point, let's go ahead and write it all out since it's pretty simple. 79.92, and we'll say, you could say joules per second, but I'm going to put it as watts since it's the more correct answer. So hopefully that was pretty simple, but then there's something else we should consider. What about using our other formula? What about our output power? What about how far or how much power is exerted by the car moving? So just the power of the car moving itself. And so we'll just call that P out, or power output. And of course, this formula is either work divided by time or energy divided by time. I'm going to go ahead and write it as work divided by time. And you might say, well, we don't know the work, but we do know what work equals, and that's force times distance. And then, of course, time stays on the bottom. And that makes this formula super easy to figure out because we know what our force and distance and time all are. We just plug in our numbers. We'll start with our force, which is 100 newtons from the car. 100 newtons multiplied by the distance, which we said very simply was 6 meters. And then, of course, the time is on bottom, is just 10 seconds. And so hopefully you can figure this one out on your own. It's pretty simple, but just in case, let's use our calculator. I'm sorry, I'm getting ahead of myself. What's 100 times 6? And of course it is 600. And then we divide that by 10. and we get, of course, 60. So our power output is very simply 60, and then we'll go ahead and leave it as watts. And so hopefully you notice that we're getting a discrepancy in our answers. Our power input is almost 20 watts higher than our power output. And that brings us to our last thing that we need to figure out, and that is our power efficiency. If you remember, our formula for efficiency is just out divided by our in, or our output divided by our input. And again, that's true for every single efficiency formula, no matter what, including power. So we can write this as our P out divided by our P in multiplied by, of course, 100. And so this is pretty easy to solve. We just literally rewrite the equation, and we put our output on top, which was, what, 60 watts? I just want to make sure I get the right color there, but 60 watts goes on top, and then on bottom we put our input, which is 79.92 watts. And then, of course, we'll just multiply that by 100. And so we'll just type this into our handy-dandy calculator because I'm bad at math, and that looks like it's going to be hard to solve. And so we get 79.92 on bottom. And what do we get? We get 0.75, and then, of course, we got to multiply it by 100. If you can't do that in your head, we can go ahead and type that in our calculator as well. And what do we get? We get about 75% efficient, which just means we lost about 25% of our power in our system, which really isn't that unheard of. That's power efficiency.